Hey everybody, I'm going to talk about Project 1. As you know, Project 1 is interfacing an LCD screen. You have to print out two messages. One is a hello world message. Here, I'll blow up the screen. It's a hello world message. And then if a button's pressed, you just display a second message. Just be aware that for grading, just doing that and writing a good report can only get you 90% of the grade. You need to do an addition, such as creating custom characters on the LCD screen, or like a choose your own adventure game, or something like that. I actually like, if I had to suggest something for practicalness, the nibble mode is actually very useful. You only have 20 pins that are available to you on the ATmega, on the Uno. And so saving by going to nibble mode, your data bus is only 4 bits wide rather than 8. So how do you get started here? Well, we'll take a look at some resources here. You may not have this particular LCD, but all LCD 16:2 LCDs have the same controller. And every time we write to it, we're going to need to perform this waveform. We need to make RS either be high or low. RS is going to be low for commands and high for writing characters to the screen. RW is always going to be low for writing, versus reading from it will be high. E will have to go then low, high, low. And we put the data bus here before the falling edge. We put some data on the data bus before the falling edge of this E here. Okay, so we need, and basically what this falling edge does is it latches the data into the LCD screen. So this can actually be quite tricky. We have to implement this waveform, and it's got a lot of timing constraints. However, we'll notice a lot of them are pretty small, like TSU, TF, TH. TSU is 40, TH is 10, TSU is 40, and those are all nanoseconds. And if our ATmega is running at 16 megahertz, which is 62.5 nanoseconds per clock cycle, we don't even have to worry about delays that short because our microcontroller can't do anything that quickly. So the only delays that we have to worry about here really are, well, we have to sequence them correctly. We have to make these happen first, and then E go high, and then put the data on the data bus, and then E go low. But we don't have to worry about the delays so much. The only exception being TW here, which is 220 nanoseconds, greater than 62.5. Or also this enable time here, TC, where you can only make E go high every 500 nanoseconds. Okay, so so that's kind of how the operation of the LCD controller works. There is an initialization sequence. You turn the power on. We've got to wait 20 milliseconds. We do this with a software delay. And then we've got to do set function. And if we go to this table here in this data sheet, this is the Digilant data sheet that's linked in Project 1's description. We can see, okay, here's the function set. That's the first step here. And if we scroll to the top here, we see RS here is 0 for all controls. Notice down here we're entering characters, and that's when RS is going to be 1. RW is going to be 0 for writing. So we're writing this function set command. And then DB7, 6, and 5 are 0, 0, 1 respectively. DL here, we're going to choose an 8-bit interface, so it'll be 1. N will be 1 for 2 lines, and F will be 0 for 5 by 8 dots. So that will be 0, 0, 1, 1, 1, 0, 0, 0. Okay. And so we'll need to figure out how to get that data, which is 38 hexadecimal, is going to show up on the data bus here after E goes high, but before, and TSU time before E goes low. Okay, so now let's take a look at how we potentially would wire this up. Here's our ATmega here. It's got port, I'm going to use port B0, port B1, port B2, and then port D, all 8 bits of port D. and I'm going to connect them to the RS, RW, and E signals of the LCD screen, as well as the data bus in the LCD screen. Now there are a few other connections that you'll need to make, like power and ground, and maybe contrast or backlighting, depending on your LCD screen. And I kind of chose these at random here, or just arbitrarily. You could choose port B5, if you could put this on port C, although there's only 6 bits on port C rather than 8. This is really the only convenient 8-bit port, but you have a total choice of 20 different pins that you could connect, and you need 11 pins over here to be driven by the microcontroller. So that mapping is up to you, and this is just an example. So I'm going to use port B0 as RS, RW, and E. And then let's see, I will, so if we keep this in mind, and I'll shrink this a little bit, and then I will open up a text box here so I can type on this thing. And what I'm going to do now is maybe write the code for this. And the first thing we need to do is we'll need to set up port B and port D as outputs. And so the first DDR-B, since the data direction register, if we set that bit within port B, DDR-B, it's going to be an output if we set it to 1. So I'm going to set this equal to 0B, 00C45, then 111. Port B0 being the least significant bit, port B1 is this middle one here, port B2 is this top one here. And so I'll actually write a comment here. I'll say the top 3 bits will be E, RW, and RS, and maybe I'll make this window a little bit larger. Okay. And then, let's see if I can edit this thing. And then I'll want to do the same thing for DDRD, and I'll make this equal to 0xFF, FF being all ones, and that's hexadecimal. And so that turns this port D into an output. Now I've done that, if we go back to the data sheet real quick, we can see that once the power is turned on, we got to wait 20 milliseconds. I will actually suggest, at least initially, that you use a much larger delay, just for and then once you've got everything working, you can tune down the delays to make it go a little bit faster. But so I'm going to use the underscore delay, _MS, and I'll make that 20. Maybe I'll do 40 milliseconds, even though it says 20 in the data sheet. And then I'm going to do the function set. Okay, function set. Again, we looked at this table here, and it turned out to be 38 hexadecimal, if you remember correctly. And that's what's going to be on the data bus when we do this waveform here. So first I need to make RS and RW go low. Here. So I'm going to make, to do that, I write out port B. So port B, I'm going to set this equal to, I'll spell it out in binary, 0, 0, 0, 0, 0, 1, let's see, 1, 2, 3, 4, 5, 6, 7, 8. And so this makes, I'll just kind of shorthand it, 0, 0, 0 for E, RW, and RS respectively. Okay, and so now I have all of those lines low. And if we go back to the waveform now, we need to make E go high after TSU time, but like I mentioned, TSU is less than 1 clock cycle. So as long as we just put it on the next C code line, it will work just fine. So I'll do that. Port B now is going to be equal to 0B, 1, 2, 3, 4, 5, and then E is the next bit, so then I want to make that high, then 0, 0, semicolon, and I'll put a comment here of 1, 0, 0. Okay. And then I want to, let's see, it looks like I'm going to put some data on the data bus, and it's got to be TSU time before it falls. Well, TSU1 time again is 40 nanoseconds, so not a big deal. So I will go ahead and do that. If you remember, then the function set is 38, so that is, where is that? That's port D is equal to 0x38 hexadecimal, and so that's the function set. And then I need to look at the data sheet again here and see the waveform. I need to wait TW time before I can make it go low. Let's see how long TW is. It's 220, which is greater than 1 cycle, so I'm actually going to put a delay in there. And again, I'm going to make it a little bit larger than normal, than it absolutely has to be. And so I'll just put underscore delay underscore US, and I'll put 1 microsecond delay there, and I'll just comment it saying this is TW delay. Okay. And now I can make E go low again. So port B equals 0B 1 2 3 4 5 6 7 8 semicolon, and that's 0, 0, 0, right, for E being low. And then I'm done with a function set. And so you could actually imagine then instead I can write this as a function in here. And so I'm gonna, let's say I'll add a function here, and I'm gonna call LCD write command of 0x38 and semicolon. And so somewhere else I'm going to have LCD write command of char command, and in here will be all of this, and then command, instead of 38 I'll have command there, and then like this. And so of course if this is all in main somewhere, right, so main, this guy, this delay, and then this command here, and of course I'll probably, since this function is after main here, I'll need a function prototype here, and this is a void, and so that looks like it. Let's see if it, apparently I can't just tab everything, so hopefully this makes sense. So those are my two, let's see if I can move the text box too. I'll just move the diagram up. Right. So now that I've done 30, this is the function set command, and now I'm going to need to do the next one. Else, there's going to be underscore delay. I check the delay real quick. The delay for between function set and display set is 37 microseconds. So now I'll go back to my code. So underscore delay underscore US, and I'm going to double it up, so I don't know, about 80 microseconds maybe. And then I'm going to LCD underscore write underscore command of 0x, I don't know, whatever it is, question mark for display set, where you have to set up the configuration of the display. So that's kind of the idea here. Notice that the only difference between writing commands and writing data is that, well, we can just cut and paste this code here maybe, and so we can just char maybe, and the only difference here is that RS, ERW and RS now is going to be high all the time. Right. And this is the E bit, and we're still writing, so this is always low. So that's the only difference between this command, except we'll do character. Probably just do that. So that's it for the coding part. Hopefully that makes sense. A couple of things to watch out for, or resources. On PolyLearn, there's actually there's another data sheet. Let's see, let's find it. PolyLearn. There's another data sheet here. Like I said, all the controllers are the same, so the commands are pretty much the same. This one's kind of nice because as you scroll down a whole bunch, they have a lot more detail on what each of the functions do. But you'll see there's like a very similar table here. The waveform diagrams, we already went past them, they're the same. But the biggest thing is, if we want to do 8-bit interface mode, it spells out exactly what the steps are a little bit better, I think. And notice some of the delays are a little bit larger too. So that's one thing to watch out for. Let's see, what else? The pins themselves, you can look them up here where they're connected. So, you know, port D, 7 through 0 are right here, and they're digital pins this on the Uno board, so you know where to wire it up to. If you want to take a look at the schematic for that, please do. A couple of other things. You will find that if you use port D, pin 0 and pin 1, they are actually connected to the USB on the Arduino Uno board. So these two pins right here, they're connected, and what happens if you plug your LCD screen in there, since it's trying to program it through the USB and it's connected to those pins, and then you put something on there, you're capacitively loading those pins, and you may interfere with programming. So to actually program it, you may have to unplug those two pins from your LCD and then plug them back in and reset the board to get the LCD to boot up. So watch out for that. A couple other things. Watch the pinouts on these LCD screens. If you have one that looks like this from SparkFun, there's a plus minus on the back of the board there. I believe those are backlight and the backlight. Pin 1, there's a little silk screen over here. For some other more different boards, it may be hard to find as well. So hopefully that makes sense. That's a good, and we'll get you started on the first project. Thanks.